What's going on, guys? Today I'll be talking about the examples of Routh criteria. Here I'll be giving one example of all the three cases, the basic standard Routh criteria and the other two cases. Apart from that, I'll also include some examples where you can see how we'll use Routh criteria in some other in some other topics. So I'll quickly go through the examples. Okay, so this is my first example, standard Routh, where you can see there is a system given. This is open loop GS open loop gain, and this is the feedback. So G into HS will be same as 200 divided by S into S cube plus 6S square plus 11S plus 6. Now somebody asked that number of poles of J omega X. Find the number of poles which are on J omega axis, left half or right half of a S plane. So I calculated, given system is this, so I calculated total transfer function CS divided by RS. Remember guys, whenever the system or open loop is given, open loop transfer function or the system is given, you always have to work with closed loop transfer function TS, that is CS divided by RS. Okay, so now I'll go to the algorithm. So TS is given as 200 divided by S to the power 4 plus 6S cube plus 11S square plus 6S plus 200. I only added the numerator in the denominator, you can see, to make transfer function since it is a unity feedback. Okay, so this is the Routh table. Here you will calculate 1 1 11 1 200, 1 6 11 6 200, 6 6 are cancelled, so that 1 1. Similarly, when you will go through this, you can see in first column there will be a sign change. Two sign changes are there, positive to negative, negative to positive. That's why this implies two poles are in right half of S plane, and which implies further that a system is unstable. So this is basic example, some standard Routh criteria. Now I'll go to the second example, which is Routh where 0 in the first column. Now you can see this is the transfer function given. If you remember, we discussed two cases, two method of solution for this case. One is with using epsilon and all, and the second one was reverse coefficient one. Okay, so I am using reverse coefficient because I want to show something extra in this method. Okay, but you can go through that first method also. But I personally like this method. Okay, so when you'll go when you'll use second method, so I'll start from here 1 2 3 2 1 2 3 2 3 2 3 2. Okay, now when you'll solve further, you can see again I am getting 0 in first column. In spite of using second method, again I am getting 0 in first column. So I'll replace it with epsilon and I'll further continue. Then what will be the difference between the first and the second method? That it will be easier to work with. In first method, if you will use, there will be quadratic equations and the equations will be long, and you can make some mistakes during the calculations also. But when you will use this method, even if you will find a 0 in first column, you can substitute epsilon and continue working on, and it will be easier than the first method. By the way, how you will get to know that whether the 0 will come in first column or not, that you have to, that there is no other way than solving it. When you will get a 0 in first column, then you can choose whatever method you want to do, but before itself you won't be able to figure that how to get whether in this transfer function you will get a 0 or not. So that you have to take in mind, that you have to keep in mind. Okay, so this is it. So you can see there is when you will put epsilon, I will take positive, epsilon is equal to positive 1. So you can see there will be a sign change because 2 minus 4 divided by 1 will be minus 2. So there will be a sign change, there will be a sign change, positive to negative, negative to positive. Two sign changes are there, hence the system is unstable. Okay, so that's how you will do it in second example. I use this method just to show this part, that you can still get a 0 in first column and how you will proceed. Okay, so that's it. Now I will go to third example. So this example is about when you will get zeros in means zeros in full row, means entire row you will get a 0. This is a transfer function. You can see this is s to the power 8 and you can given as this, like this. So when you put the coefficients like this and you will further solve, you can see I have cut these numbers because this can be divisible by a single number, so that the complex calculation will be easier. So likewise I proceeded here in s to the power 5. I got 0 0 0 0. So here my auxiliary equation will become like this: s to the power 6 plus 8s square plus 32s 8s power 4 plus 32s square 64. Okay, now this is my auxiliary polynomial. And to further solve my table, I differentiated this polynomial and put the coefficient here: 6, 32, 64, 0. Okay, then this can be cut by means this can be divisible by 2. So I have wrote 3, 16, 32, then 0. Then further we will continue. So that's how you will complete the table. And you can see there is a sign change here, then there is a sign change here. Okay, so now you have to be careful during the interpretation. Okay, total there are 8 roots. Okay, you can see s to the power 8. So there are 8 roots. So now these 8 roots will be divided into 2 and 6. Why? Because my auxiliary polynomial is s to the power 6. So I have to see above and below it. Okay, so when I saw above it, 8 roots are there and 6 will be giving even 6 is s to the power 6 is an even polynomial. That's why it will give a pair, means pair roots, in the roots in pair about origin, symmetric roots about origin. Okay, so we can see the remaining 2 roots we'll check out by going up from 6 s to the power 6. So we can see these 2 are positive. First column is positive and positive, there is no sign change, hence the 2 roots will be in the left half of s plane. That's why these 2 root automatically comes in left half of s plane, since all positive above s to the power 6. Okay, now the remaining 6 roots, this is an even polynomial and symmetric about origin, so we know they will exist in pair. Okay, so we have to check. Now how we will check? You will go down from s to the power 6. So you can see there is 2 sign changes. 2 sign changes means two roots will be in right hand side of s plane. So 2 sign changes, hence 2 roots will be in right half of s plane. Since they will occur in pair, so because of that 2 roots will be in left half of s plane, to just make sure that these are occurring in pair. Okay, so total 2 roots already, so 2 roots were already in left half. Because of this 2 roots are in right half, 2 roots in left half. Okay, so out of 8 we know about 6 roots. Okay, so the remaining 2 roots will be in the j omega axis. Okay, because there is no other place for making a pair. Okay, so you can see the j omega axis so you can see this is the final root, closed loop transfer function poles will be given as like this, where these roots can be calculated by equating this equation equal to 0. You can see that you will get one s equal to 0 and 2 complex roots. Okay, so since s equal to 0 will not make an pair, hence we will take complex roots. So complex roots will be this we got it from these 2 roots, we got it when we will come down from s to the power 6. Since these 2 roots are there, this will occur in pair, that's why these 2 roots are here. So total 1 2 3 4 5 6 are done. And when we went above this s to the power 6, we find that everything is positive, hence 2 roots will come in left side. So total 8 roots will be given like this. So that's how you will figure out the location of poles in case 3. Okay, so now I'll go to the next example, which is stability design, what I was talking in first video of Routh Hurwitz criteria. Okay, So in stability design, the one transfer function is given. You can see k upon s cube plus 18s square plus 77s plus k. Here k is variable. Something we are given is k is greater than 0. And then find the range of k so that system is stable. So we have to find the range of k so that the system will be stable. Now you can see I used Routh-Hurwitz criteria. Here I made a table, and now for the system to be stable, we want every element in the first column should be positive. Okay, so that's our criteria of stability. So you can see this is positive, this is positive. For this to be positive, it has to be greater than 0. This has to be positive, this is greater than 0. So we got it from here that k should be greater than 0 but less than 1386. But we don't know, since the k is greater than 0 it is given, hence k equal to 0 will not come into the picture. But we haven't checked k equal to 1386 whether it will come or not. So we will check here. Put k is equal to 1386 in S1. Here you will get 0. Here also 0. Here also 0. So you will get entire row 0. So you will differentiate. You will take the polynomial above it. 18s square plus k. 18s square plus k. K was 1386. Differentiate 36s. We made another Routh-Hurwitz table. There we got 36, 1386. So now everything is positive. Positive, 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 positive. Hence k equal to 1386 will also come into the range. So final answer will be 0 to 1386 with that equal to sign. Okay, so that's how you will design a system, and there comes the importance of Routh-Hurwitz criteria. It is very helpful in designing a system with a variable parameter. So you can see that in this example how easy it is to solve for this kind of questions. Now I'll go to the next example. Okay, so this is the example where I have used Routh-Hurwitz for factorizing a polynomial. Okay, so given is a polynomial, you have to factorize the polynomial. That's the question. Now I used Routh-Hurwitz table. Here it is given. You can see normal process. Here since 0 0 came in S1, so I replaced it with the auxiliary equation, differentiation and everything. This is normal process. So when you will complete this, you can see this polynomial, this auxiliary polynomial will be a factor of original polynomial. So then you can divide 1 by 2. This is 1 original polynomial, this is 2 which is auxiliary polynomial. You will get something like this. This is original polynomial is equal to multiplied this is the factor and this is the quotient. So quotient you will get. So you can write it like this. This polynomial can be written as product of these two polynomials. Okay, now these two polynomials are the roots of this polynomial you can easily find s plus j 3.16, s minus j 3.16, and for this s plus 1.5 plus j 4.21, s plus 1.5 minus j 4.21. So that's how you can factorize a polynomial into its roots. These are the roots of this polynomial. So sometimes it comes in handy to use Routh-Hurwitz criteria to factorize a polynomial. So in my final example, I will talk about state space model stability. As you can see, we can use Routh-Hurwitz criteria to check whether the state space model is stable or not. You can see I have taken an example where x dot is equal to ax plus bu, y is equal to cx. Okay, so where now this is the model given. We have to check whether this model is stable or not. So what we'll do first is we'll form a matrix called Si minus A, where Si minus A is just a identity matrix multiplied with S. So this is Si minus A. So Si minus A will be this. Okay, and A is this matrix. So Si minus A we have. Now we will calculate determinant of Si minus A. That will give you s cube minus 6 s square minus 7 s minus 52. Now we have to check whether this polynomial is having any root on the right hand of the S plane. So we've used Routh-Hurwitz criteria. You can see I've made a table. Here you can see in the first column there is a sign change between first entry to second entry. and after that it is negative only. So the total there is one sign change, which implies one root will be on the right half of S plane. That's why the model is unstable. So this model is unstable, and we have calculated by using Routh-Hurwitz criteria. If you are bothering why we have used Si minus A, here I have given an explanation. So as you know, state space equations are written in form of this: x dot is equal to ax plus bu, y is equal to cx plus du, where x dot is equal to differentiation of x. So that's why this is the general form of state space model. Okay, if you will take Laplace transform in both the sides, in both the equation, you'll get sfx minus x0, which is the initial value, is equal to axs plus bus, ys is equal to cxs plus dus, and usually x0, this, and d are 0. Okay, so I have assumed these are these 0. Then if you will rearrange these two equations, you will get ys divided by us is equal to csi minus a inverse b plus d. Since d is 0, so equal to csi minus a inverse b. Now inverse can be written as adjoint of the matrix divided by determinant of the matrix. That's what I have written. Si minus a inverse will be written as adjoint of si minus a divided by determinant of si minus a. Now you can see this is the transfer function and this is the denominator part. So poles of the transfer function are given by determinant of si minus a. If you want to know the exact poles, exact location of poles, you can do si minus a determinant is equal to 0. And from this equation you will get the roots where it is lying in the S plane. Okay, and this is also the eigenvalues of the A matrix, this A matrix. Okay, when x0 and d is not equal to 0, then you will get ys is equal to si minus a inverse x0 plus c si minus a inverse b plus d us. Okay, here also you can see ys divided by us will be this c si minus a inverse b plus d. If you will open this si minus a inverse, like adjoint of si minus a, determinant of si minus a, and take LCM, you will get finally this expression: c adjoint of si minus a b plus d into determinant of si minus a divided by si minus a. Here also you can see, if you will consider if these two are not equal to 0, then also ys divided by us containing the denominator as determinant of si minus a. That's why overall determinant of si minus a inverse determinant of si minus a will give you the location of the poles. Okay, so that's why we have used here si minus a, and determinant is this s cube minus 6s square minus 7s minus 52, and we are not interested in exact location of the roots. That's why we have used Routh-Hurwitz criteria. And you can use if you want to know the exact location, you can equate this equation polynomial equal to 0, and you can find the roots, so that you will get the exact location. So that's all, guys. So this is the application of Routh-Hurwitz in state space model. So from my side, this will be the end of Routh-Hurwitz criteria. And if you feel like I should include something else, or I've done any mistake, then please let me know in comments. Okay, and I'll see you guys later. Thanks for watching.